This week, you are taking data for a lab, and that is the moment of inertia lab. And what I'm going to do is I'm going to talk about the pre-lab. Now, for those of you in the room who took lab yesterday, you're like, well, that did me nothing good, but at least you'll see what's going on and can figure it out. So, in the moment of inertia lab, you have a big disc, and underneath it is kind of an axle, and around the axle is some string. Now that string is looped over a pulley and is hanging using a hanging mass. Now it falls a length h. So what happens is you have, well, first you got to figure out some friction stuff. I'll leave that for the lab. But in terms of the lab experiment, the initial velocity of this thing is 0. And you let this thing fall a certain height. And you record it. The time t with the stopwatch. So you have an object that falls a particular height L, starts with an initial velocity 0. What can you do with this information? Well, remembering test 1 material, this sounds a lot like a one-dimensional motion problem, where x naught, v naught t, plus 1/2 at squared. Now what I did is I set the starting position as 0, and I have declared, this is similar to an Atwood's machine, that up is negative and down is positive. So because of these initial conditions, x naught is 0, v naught is 0, and you're left with a way more simple equation. X equals 1/2 at squared. The point in the pre-lab, the first point, is determine A. You're given t, and in the lab you'll measure t, and you're given x, that's the vertical height. So what you do is 2x over t squared is equal to a. And all you do is you take the height that's listed. They give you the height in the pre-lab as 75 centimeters. The thing that you need to remember is that we are using meters. So convert that into meters and then plug it in to get acceleration. So time is in seconds, whatever they give you for time, and you're ready. Now the next step, so this is determine A, that's part 1. Part 2 is determine alpha. So for alpha, that thing, the string is being pulled off that spool at a particular rate, and that rate is increasing with the value A. And in physics, you know the relationship between V and omega. V is omega R. The equivalent equation for angular acceleration is A is equal to alpha R. So just as you can get a linear velocity from the rotational or angular velocity, you can get a linear acceleration from the angular acceleration. And it is important to keep track of R. So in from above, you have the big turn wheel, and then you have the axle. And the acceleration is coming from this circle, or from this string, which is tied around this axle. The R used to determine to determine alpha is the R of the axle with the string. The string is wrapped around, oh, that's a horrible S. String. So the string is wrapped around the inner axle, not around the outer axle, so, or the outer circle, or whatever you want to call it. So the R used is the smaller diameter divided by 2. They give you two diameters. They give you the diameter of the big wheel, and then they give you the diameter of the axle. Use the diameter of the axle because that has the string wrapped around it. And then you have to divide by 2. Why? Because radius is the diameter divided by 2. Well, why not just determine radius to start out with? Well, it's difficult to find the radius of an axle, but it's trivial to figure out its diameter. They're going to give you vernier calipers. We remember our vernier calipers, don't we? And you just take those tongs and wrap it around the axle, and that gives you the diameter of the axle. Divide by 2, now you got radius. You're good to go. So now we have alpha. So that alpha you take A divided by R. So you get the A from part 1, divide by 2, or I'm sorry, you divide by the radius, which is the diameter divided by 2. And then you've got alpha. What was the next part? Oh, I got to determine, what's part 3 on the pre-lab?
I ain't got that far yet.
I haven't gotten that far yet. Who's got a pre-lab? Tension? Okay, I got that. So in tension, that mass is hanging from a string. It looks a lot like the Atwood's machine. And if you're looking at just the forces on that string, you've got the mass of the object times gravity pulling down, and you've got tension pulling up. And the goal is find that tension. Now, there are a lot of other things going on in this problem, but one of the advantages of, or one of the things that you do in problem solving with physics is that you can focus on just a narrow part, and if you know all the components, you can solve for whatever is missing. Here, we're going to use the same Atwood's machine axes, down as positive, up as negative. And we know Newton's second law, sum of the forces in that vertical is equal to MA in the vertical. Now T is up, which is in a negative direction, and mg is down, which is positive. I know what A is. We can get A from part 1. We're given mass. We know we're on the planet Earth. So because of that, we can get a tension. Tension, mg minus may, or mg minus ay. And that's the tension in the string. Now, for part 4 and 5, I'm not sure what the purpose of point 5 is. I'm not quite sure. But 4, what's the torque by the tension? So torque, since this is looking from above, that tension on the string is at a right angle to the radius on the axle. The torque is the tension times that radius on the axle. The radius is the distance from the rotation point to the point at which the tension is pulling. In a way, it's kind of like those rocket problems that we've dealt with before. So the tension comes from part 3, the radius you've measured before, and you have the torque. And make sure that when you do all this stuff, the torque kilograms meters per second squared. Maybe. Yeah. Times meters, yes, thank you. Maybe I could say I wasn't done yet, which would be wrong because it's 8 a.m. and I can't think. So you get this, and you just leave it like that. Now for number 5, they want to know the net torque. And I would say, since there is only one force, they explicitly stated that there was no friction in the apparatus of the pre-lab. Yay, no friction. And since there is only one force, there is only one torque. So the sum of the torques is just that, whatever answer that you get from the 4th part. And that's it. That's the pre-lab. I knew I was going to have to go over this when, over a course of 45 minutes, 4 consecutive people with 5-minute gaps came in and wanted me to do the pre-lab. So I was like, I'll just come in and do it for lecture. Question in the back. I don't know. See, here's the thing, and very passive-aggressive question. Let's respond with a passive-aggressive answer. No, not really. I'm going to respond with truth. One of the questions asked yesterday was, what's the deal with the pre-lab? Like, do I get points for the pre-lab? The pre-lab is based on completion, not correctness. The pre-labs are only asking for you to take a stab at it. So the only way that you'd get penalized is if you don't do it. So I make the joke when I really first learned about how labs are run, I was like, you could sit there and draw little pictures of trees on your pre-lab and they'd still have to take that into consideration and give you credit. Don't test them by drawing little pictures of trees. So the fact that you didn't hear this until just now, I really don't think makes a big difference on the score of your pre-lab. If you just turn it in, you get credit for it. And in the end, those pre-lab scores, if you don't do it, they take away 15 points from your worksheet. That's the only thing that happens. So effectively, it's 15% of your worksheet score. So I understand the point, but most people get hundreds for pre-labs anyway, and the only way they don't get 100 is if they don't do it. So, what's going to happen is you're going to put by varying the mass, you will see that A changes. Now, really what's going to happen is you're going to have a mass, you're going to have a time, you're going to have an A. And what's the one thing that we know about moment of inertia with what equations that we use? The sum of the torques is equal to I alpha. So in this list of information, you're going to have, let me redraw this. You're going to have mass, you're going to have time, you're going to have A, you're going to have alpha, you're going to have torque. And what you do is you plot torque as a function of alpha. And what ends up happening is that you fit a line. Now, you're going to fit two sets of lines, and for each of these, the slope is equal to the moment of inertia. So you're going to get your fitting software. Since this is a formal lab report lab, you'll take it home and do it there. And there are two major setups of this. One is for disc only, and then the next is disc plus 3 masses. So on the first time, you're just going to have that plate that rotates. On the second part, you're going to put 3 big copper masses on that plate and then spin it around again. And what you should see is the moment of inertia that you're going to get for the first one plus 3 times the mass of these points times r squared is equal to the new moment of inertia that you get for stage 2. So this is determined stage 1. These are, when you look at them, you go, well, they're cylinders. Don't I use the parallel axis theorem for cylinders and then move them outward? Yes, you could. But but it's not a problem. It's just that if you do the math on taking a cylinder and rotating it around versus taking a point mass and circulating it around, the answer that you get for both is within like 99% of each other. So it falls within that. The bigger errors are student related, not the fact that this thing was off by 1%. Yes?
So in the first graph for part 1, there's like 2 different masses, so you have 2 different columns.
Well, they're two. You're talking about the masses that you hang.
There's like part A and B.
Part A is when there's no masses on the plate. Part 2 is when there are 3 masses on the plate. I don't think they have you put 1 mass, then 2, then 3.
There's like first 150, 30, second 100.
Well, for that part, that's the mass that's hanging on the string. That's the part that is this, which will be that hanging mass column. So when they have you adjust the mass, go from 50 grams, 100 grams, 150, those are those steps. But the first data set like this, you'll get one line for just the plate only, and then you'll get another line for 3 masses on the disc. And really, talking with the students before lecture, they seem to think it's a long lab. If you know what you're doing, you can get in and out in about 45 minutes, including quiz and exam. Mostly because all of the analysis is done at home. All you got to do, all you really need to do, you don't need to do any analysis whatsoever in the lab. You get those masses, you get those times. You first do it on the plate only. You do 5 or 6 masses. Then you put the weights on. You do 5 or 6 more of them, and then you're done. That's the only data that you need. So, and then you can continue on with your life. So that's it. Go ahead. Oh.
Dr. Eschenberg?
Yes.
I saw on the experiment calendar that after Thanksgiving break it says to be announced. Do we not have any more experiments?
It is the discretion of the instructor of record, me, to decide what to do that week. Most likely, just so we get some appreciation from the room. When I was a TA, we used that week as an experiment or a lab final, where you would go in, you would take an hour-long test, and then you would do an hour-long lab, and then that would be it. But we've decided against that. I'm nice. I'm a giving guy. And so what we're going to do that particular week is, for all the people who have had legitimate reasons to miss lab, there's only like 3 or 4, because only 3 or 4 people have had concussions. They'll make up the labs that week. And then everybody else, you don't have to go. I don't know. Because I don't want to be there. The TAs don't want to be there. The lab physicist doesn't want to be there. No one wants to be there. It's the last week. It's dead week. I understand. So we're not going to do anything. That's the plan. So I'll gladly accept your thank you cards after class. So, are you happy?
I'm blessed right now.
Are you-
Trying not to cry.
Okay. I don't have any tissue up here. We're gonna
It's
have to-
fine.
Okay.
I'll set it up.
All right. So that's the lab for today. Any questions? All right. Now on let's see, what do we need to do? So in we've got to add a particular type of problem into our resume or repertoire.
How come we didn't get the whole acceleration equation for the last test?
How come you didn't get the whole acceleration?
Like the A is alcohol.
I don't think it was necessary. It wasn't. If it was the Fish of Fury, it would have been necessary, but not this.
This seems pretty nice.
It would have been nice, but unnecessary. So, all right, let's move on to other things. In a particular event, if you had just a mass hanging and I wanted to know the tension of that string, you would go, well, that's easy. The tension of the string is just the mass times gravity hanging down. And I go, well, how do you know this? Prove it. And you would say, well, the thing, is it moving? And I'd go, no. You say, fine, the sum of the forces vertically is equal to 0. There are only two forces acting on this, T minus mg. So the tension is equal to mg. And we've done that before, and it's something that it just makes sense. Now let's add a little bit of a twist to it. Well, how about this? I have a 5 kilogram mass, and the center line is a dotted line. And both of those thetas are equal to 30 degrees. And the question is, what are the tensions in the string? Now things get a little bit more complex, slightly. One of the things that the student can ask again is this thing moving? And I go, no, it's not moving. At which point, yes, it's not moving. If it's not moving, you can say that the sum of the forces in X are equal to 0. And you could say that the sum of the forces in Y are equal to 0. Now over here, the sum of the forces in X are equal to 0, just as this example. But the big difference is this equation is boring. There are no forces acting in the horizontal, so why bother writing it down? So we skip it. Here, there are forces acting in the vertical and the horizontal. The thing that we have to know is there is one force pulling down on this, and then we have two forces pushing or pulling up. Now, each of these forces, what we need to do is we need to break them down into component parts. Oh no, you're going to have to recall something from the beginning of the semester. Those force vectors are coming off at angles. So what you need to do is you need to convert it into their horizontal and vertical components. So this is F1x, F2x, F1y, F2y. So those forces, this one and this one, your first goal is to crack them into two parts, into their components. their horizontal components and their vertical components. Well, let's look at this some more. Well, what are my vertical components? My vertical components are F2y, F1y, and mg. Those forces are equal to 0. Now for F2y and F1y, and this is one of the reasons why I don't use g as -10, I use g as a magnitude, is that I look at this and I go, well, F1y and F2y are both up. So they're both positive. We have to set up our coordinate system, because it's 2D, we have to set it up sensibly. And set it up this way. So there is one force down, mg, and then there are these two. The next one, sum of the forces horizontally, is also equal to 0. F1x and F2x. F1x is to the left, F2x is to the right. So sum of the forces horizontally is equal to 0, which is equal to F1x, or minus F1x plus F2x. So F1x is equal to F2x. Now let's take a look at the angles. Now, I've kind of made it easy in the sense that the angles are the same. So sine of theta is equal to F2x over T2, opposite over hypotenuse, and it's also equal to F1x over T1. So F2x is equal to T2 sine theta, and F1x is equal to T1 sine theta. So taking these and substituting it into here, I get T1 sine theta is equal to T2 sine theta. Now, one of the things that you can make as an observation is the signs cancel and T1 is equal to T2. So because those angles are the same, it simplifies, and you know that the tension of 1 is equal to the tension of 2. So all we got to do is we got to find one of the tensions, and then we have everything. Another question that we could do is, or one other problem, is use the vertical. 0 equals F2y. Cosine theta is F2y over T2. So T2 cosine, oh, that's a horrible thing. Cosine theta is equal to F2y. And you could do the same thing and say T1 cosine theta is equal to F1y, using the same logic of trigonometry or rules of trigonometry that we used before. So 0 is equal to F2y, T2 cosine theta, plus F1y T1 cosine theta minus mg. What I'm going to do now is I'm going to do a substitution. 0 equals T1 cosine theta plus T1 cosine theta minus mg. Or mg is equal to 2 T2 cosine theta. What I did was I moved the mg over, and then, whoa, at least I should be consistent with the substitution. So mg is equal to 2 m1, or I'm sorry, mg is equal to 2 T1 cosine theta. So mg over 2 cosine theta is equal to T1. M is 5, G is 10, there's 2 cosine of 30. And I'm left with 28.9 newtons. Yeah, I'm going to move it up just a wee bit. Okay. So that's 28.9 newtons. And so that is, it's a, I mean, you could kind of, it's very similar to a torque bar, but without the torque. So what this is an initial problem that builds up to something else. And in the long game, I'm going to introduce a new word. And in 213, they're called hybrid problems. In MCAT, they're called passage problems. The origin of the hybrid problem came about 3-4 years ago, where, open this up just a wee bit. It came about 3-4 years ago when I just wanted to be mean to the class. And so what I did was I took several different spheres of knowledge of physics that we've covered and I merged them together. And initially, the problems that we cover tend to be very simple. Why? Because we just started. But physics is actually a combination of all sorts of stuff going on. You've got rotation and ballistics going on at the same time. Just look at a baseball being thrown through the air. What we're doing is we're taking very small steps, and we're now finally able to begin to merge stuff together. It was unintentional, but people started coming back from the MCATs and said, your class was MCAT prep because those freakish, bizarre problems that pulled in like all these different things together, we did that in the MCAT. And I think that it's a very good exercise. We won't have a hybrid problem today. We will start thinking about it on Thursday. But I just wanted to get the word out. You will hear the word hybrid problem and you will know what that means. In the next type of problem, this is very similar to what exercise science students will deal with. You have now, I don't know biology. I don't know the distances of all these arm parts and biceps and stuff like that. So the numbers that I have are just merely kind of, okay. What? And definitely not to scale. What we have is a simplification of a arm with a bicep. For those of you who are taking biomechanics, you're going to be doing this next semester. If you're exercise science and you're going to take biomechanics in the spring, take my notes. You're going to be using them all over again in biomechanics. I asked, biomechanics is a 400 level course. I think it's a course suffering from low self-esteem, so they made it a 400 level course so that it feels better about itself. Because really all you're doing is basic 213 stuff and throwing in a lot of muscle terminology, or I don't know. So stuff like this is necessary. The letters are going to be different, but as I've taught you, as long as you know what they mean, you can use whatever letters are necessary. What do you know? Well, let's talk about this. You have an arm, and we'll make it massless. This is the pivot point. So it's free to rotate about that. Think of it as like a hinge. This is the load on the arm, a certain mass. Let's make it 5 kilograms. And then this T, which we're going to solve for, is the tension in the muscle that's holding up the arm. So the question is, what's the tension in the arm? The first thing that you want to do is you want to break this thing down into its components. That tension is holding up the arm. And at this particular point here, there is a force. I don't know why the light is horrible. Oh, there we go. Better. So the tension is going up and to the left. This is the tension in the Y. That is the tension in the X. The other thing that is given are those distances. Y equals 30 centimeters. And X1 is equal to 5 centimeters. So those are the distances that we listed above. And really, I just wanted to focus on that for just a moment. This angle that we'll need, we can get it from inverse tan of Y over X1. So this becomes inverse tan of 30 divided by 5. So the inverse tan of 6. Now, one thing that some people may be asking, I'm such a big fan of turning everything into meters. Why did I not turn 30 centimeters into 0.3, and why did I not turn 5 centimeters into 0.05? It's the same thing. If you're taking a ratio, doing the conversion is irrelevant because the conversions are going to cancel as well. So in something like this, just divide it out. It's not necessary to change it to meters yet. So that's the angle. And sine of theta is ty over t, and cosine of theta is tx over t. Now, had we used that as the angle, things would have changed, but we got to stick with the angle that we've determined. So t sine theta is equal to ty, and t cosine theta is equal to tx. So those are our tensions in algebraic notation. Well, why is this necessary? Because when you've got forces acting at angles, the first thing that you want to do is change everything into their vertical and horizontal components. If they're already vertical or horizontal, yay. But if they're at a weird angle, you've got to change them. With something like this, and I made it evident, there is a pivot point. If there is a pivot point, one of your questions should ask, hey, Dr. Eschenberg, you mentioned pivot point. Is this thing moving? Answer, no. It's not moving. Which means that it is in blank blank. It is in translational equilibrium. But yeah, we want, I've just thought of an interesting problem. I'll work on it later. The more important part is it's in rotational equilibrium. So if it's in rotational equilibrium, the sum of the torques is equal to 0. Now for forces like this, what I'm going to do is I'm going to redraw the bar. Here's the bar. You've got mg pulling down at a distance of x1 plus x2. And then you've got these forces. Now what I did is I drew it like this because the contact point of the string with the bar is right there. So this Tx is at the bar pushing directly at the hinge. This is Ty and it's acting perpendicular to the bar. The torque contribution of Tx is equal to 0. And why is that? Because when you look at it from this perspective, this force is pushing directly down on the hinge. So what is the distance from that force or tension to the rotation point in terms of that particular component? It's 0. It's a lot like this. For this door, obviously the best way to open the door is furthest away from the hinge and at a perpendicular angle. So if I start pushing it like this, if I'm only allowed to push down, directly down on my palm, the closer it gets to acting like this, the less torque I have to keep that door open. So pushing it closer to this reduces torque, and also pushing at an angle reduces torque. So the more it becomes perpendicular, the more you're maximizing your available torque. it's very similar to, you can kind of look at this and go, if you had a pivot point right here and that Tx pushed down right there, that torque is equal to 0. Why? Because the distance between that point and the pivot point is 0. Now granted, it is further back on the arm, but you can kind of think about it and go, well, if that's pushing right at that pivot point, it's not causing it to rotate. It's just causing it to be forced into the wall. And so that's the explanation. We have two torques, Ty x1, and we have mg x1 plus x2. Now the pivot point is here, so we always go out to the force and then in the direction of the force, to the right, up, thumb out of the page, or positive. Pivot point to the force down, torque goes into the page, or negative. So that's how we determine the signs. We know what our mass is. We know what the dimensions are. What can we get from this? What's our only unknown in that equation? Ty. So solve for Ty. And then we'll get it. M was 5, G was 10, X1 was 0.05, X2 was 0.15, X1 is 0.05. Now granted, those would cancel out their units, but it's best to keep that kind of thing going on. Did I say 20? No, X2 was 15, X1 is 5, for a total of 20. Okay. So I get 200 exact. 200 newtons. Okay, next. Now that I have Ty, I can get T fairly quickly. I know that T sine theta is equal to Ty. So T is equal to Ty sine theta. So 200 divided by the sine of 80.5. .8 newtons. And so that is how you would solve a bicep problem. All right. Now, all right. Okay, I've got 14 minutes. I got one last thing to teach. So in the problem set that's at the front of the room, there's a problem similar to this, and you can go through the steps and work it through. There are a couple of more problems that we'll consider on Thursday, and on the back of that problem set is the first of your hybrid problems that you'll deal with. We'll go over it on Thursday. That's not a big deal. So the one last thing that I want to do is talk about density. There are 3 major types of density that we need to cover. They're very easy to go over, but I want to announce or make the proclamation of what these letters are. There is our typical density rho, and this is our volume density. So rho is equal to mass divided by volume. It is the one where most people are very familiar with what's going on. You've got a mass, you figure out its volume, boom, you're done. Then there is surface density. Surface density is it's not used as frequently as volume density. It is mass over area. So if you have the way that I think of it is these tiles. I don't need to know the volume of the tile, but I know each tile is 1 square foot. So if I have if each tile has, let's just say they're made out of lead, 1 kilogram per tile, then I know that the surface density is 1 kilogram per square foot. So technically, these things do have a rho, but from a practical standpoint, it just takes too long to figure out the volume of these tiles. So you just say, how much area does that much mass cover? And it makes it easier. The last one which we'll cover is linear density, which is lambda. Mass over length. Lambda will be used, rho and lambda will definitely be used for test 3 material. Lambda just gives you, if you've got a string, a meter long string, you don't want to take the time to measure its volume. But what you do know is if that string is 10 grams and it's a meter long, you know that its linear mass density is 10 grams per meter. So those are two new terms, one that we're very familiar with. But what I wanted to do is sometimes you may see and I got to go through the problem sets and purge out the letters. Sometimes you'll see rho sub L. Some people use this as linear mass density. So rho sub L is in my estimation, it is a less commonly used term than lambda. And I want you guys to use, for this semester, and we go back and forth occasionally, but for this semester, I'm going to proclaim lambda is linear mass density, straight up rho is volume density, or density. And so, that is it. I will see you guys on Thursday.
You said